we're going to have a look at an alternative way of doing multi-step methods to solve ODEs. And this class of methods is collectively known as Adams methods. So the idea is we want to use past information, for example the function values at I minus 1, I minus 2, etc., to fit a polynomial, but we're only going to integrate that polynomial over one segment, in other words the segment that we're currently trying to estimate. So let's go back and have a look at what we're really trying to do here. The ODE can be written, or the solution of the ODE can be written as an integral dy from yi to yi plus 1 is equal to some integral of our right-hand side function from ti to ti plus 1. So schematically, that's what we're trying to do there. So if we integrate the left-hand side, that's just equal to yi plus 1 minus yi, and we shift the yi to the other side, so we have yi plus 1 is equal to yi plus that integral on the right-hand side. Everything that we've looked at so far, RK4, etc., are just different ways of estimating this integral. And we're going to use a different way again in this video. So, how are we going to do this integral using the Adams methods? Well, the details depend on the number of segments we choose. And so what we're going to do here is we're going to consider n is equal to 2 segments to describe the general process. Unlike in the previous video, n here is actually equal to the number of segments. Previously, n had been equal to the number of segments minus 1. We're going to write the general 2-segment update as yi plus 1 is equal to yi, that comes from the integral of dy, plus the step size h times a times the function value at I plus 1 plus b times the function value at I plus c times the function value at I minus 1, where the coefficients a, b and c are unknown and we're going to try and estimate them. Now, for an explicit update, we don't know what fi plus 1 is equal to. So for the predictor step, which has to be explicit, in other words using information that we've already got, not information we don't have, we know we have to set a is equal to 0 because we can't use this term here. So we can rewrite this as yi plus 1 equals yi plus h times bfi plus cfi minus 1. Let's expand the right-hand side of equation 1 in a Taylor series about the time ti. Okay, so we've just written that equation there. Expanding out in a Taylor series, well obviously the bfi term stays the same. The cfi minus 1 in the Taylor series looks like that. Now let's recall that the ODE is written as y dashed is equal to f of t and y, and that obviously then fi is equal to f of ti yi. So if y dashed is equal to f, then f dashed is equal to y double dashed, f double dashed is equal to y triple dashed, etc. So let's just use that to rewrite the term in brackets up here. So we're just rewriting this using the original y. We can group the terms in this expression, so there's a y dashed here and a y dashed there, and we write that yi plus 1 is equal to yi plus b plus c hy dashed minus ch squared y double dashed plus higher order terms. Now we can also write the left-hand side, in other words yi plus 1, in a Taylor series about ti, and if we do that we get a standard Taylor series expression. Yi plus 1 is equal to yi plus hy dash plus h squared on 2 y double dashed, etc. And what we can now do is compare terms in this expression here and this expression there. So if we equate these terms, we can see that b plus c must be equal to h, minus c has got to be equal to 1/2. That gives us b plus c is 1, c is equal to negative 1/2, or if we solve those, b is equal to 3/2 and c is equal to negative 1/2. Therefore, go back to what we had originally written, and our Adams-Bashforth 2-segment update is written as yi plus 1 is equal to yi plus h on 2, 3 times the function value at I minus the function value at I minus 1, plus some terms that are order h cubed. That's our error term, that last term there. This can actually be shown to be equivalent to fitting a straight line between fi minus 1 and fi, those 2 points there, and integrating this line, so fitting the straight line between the points and integrating that line over the final segment. So you can see that the Adams method is different to the Newton-Cotes method in that we're only integrating over this last interval, even though we're using earlier information to fit a function. That's the fundamental difference with the Adams methods. So we've done a predictor, but now we can do a corrector step. Because we have an estimate of yi plus 1, we can calculate fi plus 1. So let's go back to our general two-segment update given by this formula here. Yi plus 1 equals yi plus h, afi plus 1 plus bfi plus cfi minus 1. The corrector step are called Adams-Moulton methods, and they of course assume that we know fi plus 1 from a predictor step. So if we again expand this right hand side of this equation here in a Taylor series about ti, it's very easy to show that yi plus 1 is equal to this long expression here. So that's the a term, that's the b term, and that's the c term. I've just rewritten that equation up here in yellow in the top right. Also expand the left hand side, in other words yi plus 1 in a Taylor series, and this is just the standard Taylor series. So now what we can do is we can equate this to this, because they're equal, and come up with some equations for a, b and c. So if we equate the coefficients of y dashed, y double dashed and y triple dashed, we get that a plus b plus c is equal to 1, that a minus c is equal to 1/2, and a plus c is equal to 1/3. If we solve those equations, we get that a is 5/12, b is 2/3, and c is equal to -1/12. If we go back to our original assumption about what the corrector step was equal to, we get the Adams-Moulton two-segment update as yi plus 1 is equal to yi plus h on 12 times 5 times fi plus 1 plus 8 times fi minus 1, plus an error term that scales like h to the 4th. So why would we use Adams-Moulton instead of just continually using Adams-Bashforth? Well, it's maybe not obvious, but it turns out that Adams-Moulton has the same accuracy but uses less prior estimates. So we have to store less information and do less arithmetic. Adams-Moulton also has better stability because in effect it's an implicit method. However, Adams-Moulton can't be used straight up because it assumes we know what fi plus 1 is, but we don't. So therefore, Adams-Moulton can be used as a corrector step for another explicit method, and typically we would use Adams-Bashforth as the predictor and Adams-Moulton as the corrector. We don't have to. We could actually use a Newton-Cotes open formula if we wanted to. With the Adams methods, as with Newton-Cotes methods, the predictor and the corrector should be the same order of error, otherwise we're wasting effort. Let's have an explicit look at an explicit example of using an Adams-Moulton two-segment update with a suitable corrector. So this is the two-segment update that we derived previously. The two-segment Adams-Bashforth method has an order of error that's h cubed. So this and this aren't compatible. So we need to move to a three-segment Adams-Bashforth method in order to get something which has the same order of error. And it turns out that the three-segment Adams-Bashforth method is equal to this expression here, and that AB3, which is this scheme, is equivalent to fitting a parabola to the points fi minus 2, fi minus 1, and fi, and then integrating that parabola over the interval ti to ti plus 1. So the algorithm then is predict an estimate of yi plus 1 using Adams-Bashforth three-segment. So that would look like that. yi plus 1, 0 is equal to the AB3 update. Correct this estimate for yi plus 1 using the Adams-Moulton two-segment. So in other words, yi plus 1 is equal to yi plus h on 12 times. Now, our function value estimated at our estimate of yi plus 1. And pretty much as with the Hoynes method, we can iterate on the corrector. So we can calculate yi plus 1m and substitute m minus 1 into this one here and iterate on this corrector step multiple times. Of course, we can't start this algorithm with I is equal to 0 because we don't know what fi minus 1 and fi minus 2 are equal to, so we need to use another scheme to calculate our first two estimates, y1 and y2. So for example, we might use an RK4 scheme to do the first couple of steps and then move into the Adams-Bashforth, Adams-Moulton predictor corrector. So, to summarize the multi-step methods, we've looked at two different classes, the Newton-Cotes methods and the Adams methods, which involve Adams-Bashforth and Adams-Moulton. The Newton-Cotes method fit a polynomial over multiple steps and integrates over multiple steps. The Adams methods fit a polynomial over multiple steps but only integrates over one step, the last step that we're trying to estimate. Both can be used as predictor corrector methods and probably should be. The key advantage over multi-step methods when compared to something like RK4 or adaptive RK4 is that you only need one new function evaluation, or perhaps two if you're dealing with predictor corrector schemes. So there is actually less work than RK4, but we can get the same order of accuracy. The downside is we need to store more information from past steps.